In lesson 6, we're going to look at connecting similarity and transformations together. So let's take a look at 6.1, dilation, miscalculation. So go ahead, pause the video, take a look at this, and see if you can figure out what's wrong and why GEF is not a dilation of ABCD. So go ahead, pause the video, check that out, come back. All right, so could have said a few different things here. Maybe that they're not the same shape because we kind of look like we have a square here and a wider, skinnier rectangle here. So maybe you said something about not the same shape. Maybe you also notice that the sides are not scaled, so it doesn't look like it's scaled by the same factor because it looks like kind of EG is almost the same size as AB, and then BC gets longer to EF, so not the same scale factor. Maybe you also noticed that E and F are not on the same ray as PB, so not on ray PB or ray PC. So let me kind of draw that out for you here. Okay, so maybe you noticed if you extend a ray here to go P to B, that E doesn't land on that, and we know that when we're dilating, we measure from the center of dilation to the point, and then we continue on that ray. So if we were going to dilate this, the image of C would need to land on this same ray, and the image of B would need to land on that same ray. So maybe those were some things that you came up with there. We definitely can see that the angles are still right angles. So angles stayed the same, but sides maybe not scaled at the same rate. All right, in this next one, you're gonna need to pause the video in a little bit here to look at these cards, and you're gonna sort the cards into some different categories. So you're obviously not gonna be able to physically sort them on the screen, but you can kind of write down on your notebook what cards you're putting together and why. Okay, so sort these 6 cards into a few categories of your choosing and just make sure you write down why you're putting which cards together. So pause the video, come back. Okay, so you could have sorted these into different categories. I'm just gonna do a couple that you might have come up with. Again, you could have different ones. So maybe you sorted the cards this way, and you looked at triangles versus quadrilaterals. So 3 sides versus 4 sides. Maybe you looked at congruent shapes versus not congruent shapes. Maybe you looked at dilations versus not dilations. And maybe you even considered these 2 not dilations since they're congruent. So they didn't actually change size. They do have a scale factor of 1. So they technically could be a dilation of each, or are a dilation of each other, or they're similar, I guess. They didn't actually change shape or size. So maybe these ones are dilated by a certain scale factor. These ones are not, because this one changed the angles. So these ones cannot stretch to each other. And then these 2 are congruent. So maybe you said a dilation of something other than a scale factor of 1, but multiple different ways to sort those. All right, so now I would like for you to describe a sequence of rigid motions. Okay, that's going to take a card. So let me get rid of some cards here so you guys can do a rigid motion that would, a rigid motion and dilation. So just transformations. We obviously can't do just a rigid motion here since rigid motion preserves size. Okay. So do a sequence of transformations. So translation, rotation, reflection, and dilation. So any of those that will take G onto F or F onto G, whichever way you would like to write it. So pause the video, get that written out, and then you can come back. Okay, so multiple ways that you could do this depending on how you want to start this, but you could, for instance, do dilate figure G. So I'm going to take the smaller square onto the larger one. So I'm going to dilate figure G using, and let me actually label these points so that they're easier to talk about. So let me label this like A, B, C, this way when we're writing our transformation, it'll be easier to talk about. So if you did this and you did different letters, yours are just going to be slightly different than mine because you'll be using different letters, obviously. Okay, so let's dilate figure G using B as the center. And a scale factor of, and you'd figure that out by figuring out how far. So this one's each three units per side, and this one is 12. So how do we use multiplication to get 3 to be 12? So that's by 4. So by a scale factor of 4. Okay, so then that's going to take this image, it's going to expand it. So now D is going to land on E. So then we're going to need to reflect over this line BE. Okay, so then reflect figure G over line BE. And then that would take this little square, make it large, or the same size, and then flip it over. So that's one way you could have written that. Now again, you could do this differently, right? So you could, instead, you could be dilating figure F. Okay, so this I probably shouldn't have used F's and G and F since we've got those figures, but dilate figure F using B as the center, so using that same kind of common vertex here, a point that they share. So dilate figure F using center B and a scale factor this time of 1/4. Okay, so 1/4 of 12 is 3, so we want to be making this one smaller. Okay, then we could reflect over, now E will land on D, so you can still reflect over BE or BD, whichever you prefer. Okay, you could also reflect first, so we could have reflected either shape over the line, so that it'd almost like be inside each other. Okay, so if we had this one, so if we kind of looked at this, let's see if I can rotate. So if you were to have reflected this first, so reflect it would put it here, then you could have expanded it to be the same size, dilated it to be the same size. So you could start with a reflection. So there's going to be multiple different ways to do this. So let's take a look at one of the other cards. So if we looked at card number 1, okay, and if we're going to, again, you can dilate whichever one you want. First, so I'm going to take the smaller one to the bigger one. So dilate figure ORQ, okay, which you could call G. So they're saying this little one is G. So we could just say figure G, or you could say triangle ORQ. Okay, so dilate figure G using center O. So you want to do the shared vertex so that it stays in the same spot, okay, so that it's set and then just expands. And a scale factor of, so figuring out what scale you want to use. Remember, divide what you're trying to get to, okay, by what you have, those corresponding parts. So you would divide 7.5 by 5. So when you do 7.5 divided by 5, so by a scale factor of 1.5. Okay, so that, I mean, if you're looking at fractions, that's also a fraction of 3/2, or you could even just leave it as 7.5 divided by 5. Okay, so just kind of thinking about what we did there. Okay, so that was, I'll just delete out that part. But so that was 7.5 divided by 5. And then this one actually just lands right on top of it. So that's all you would need to do on this one is dilate figure G, the smaller one, with O as the center and a scale factor of 1.5. And so if you were going to do this the other way, so if we were going to dilate the bigger figure, which they're calling figure F, this triangle PON, so dilate figure F using center O, or O as the center, however you want to write that, and a scale factor of, now you would just do the reverse of that. Okay, so now you would be doing 5 divided by 7.5, okay, and get 0.666 repeating, okay, which is a fraction of 2/3. Okay, or again, the way that you did that in your calculator was 5 divided by 7.5. So what you're trying to get to divided by what you have, so that we can dilate it down. Okay, then let's look at one more. So let's look at, actually, let's not look at this one. Let's look at one of the congruent ones. Okay, so for this one, they're congruent shapes. So this is just going to be back to rigid motions. So we're going to need, and they don't share a common vertex yet, so we're going to need to move one onto the other. And again, let's go ahead and label some points here so that we can talk about it easier. But so if we just label a few of these, and then I won't use F and G this time, so J, K, L, M. Okay, so then when we go to write these motions, okay, there isn't going to be a dilation in this because they're the same size. So we'll say translate, because you want to get a couple of points together. Okay, so translate figure F by directed line segment D. So what point goes with D? So that's DJ. Okay, so we'll move it on segment DJ. Okay, so translate figure F by directed line segment DJ. That will push it down so that D is on top of J. Then we would want to rotate figure F until, and then pick any of the points, because now they're lined up. Now D is lined up with J, so now you're just going to rotate until one of these lands on its counterpart, okay, or its corresponding angle. So I'm just going to say C lands on M. So rotate, and you can put the direction if you want to, clockwise or counterclockwise will get you there. Clockwise will be in the quickest. So then rotate, let's do figure F clockwise until point C coincides with point M. And again, you could have done until B coincides with L, until A coincides with K, whichever you wanted. But then there isn't going to be a dilation here because these shapes are congruent. All right, so then looking back at all of these cards again, so which of these did have a change in size so that there was a scale factor? And when we're doing, so this one is saying for all the cards that could include a dilation, what's the scale factor used to go from F to G? Okay, so F in this, so the ones that changed, okay, so we don't have a dilation here because that's the same size. Don't have a dilation here because those are the same size. Don't have a dilation here because the angles changed size. So we're taking a look at these three. And so when we're talking going from figure F to figure G. So looking in this one, F is that PON triangle. So here's the side in F. Here's the side in G. So remember, to figure out the scale factor to go from F to G, we take the image divided by the original. Okay, so we're going to take the image, so where we're trying to go, divided by what we have. Okay, which feels kind of backwards, but it's where you want to go divided by what you have. And remember, if it's getting smaller, it should be less than 1. So when you take a look at those two numbers, make sure you put the smaller one on top, bigger one on bottom, because we're trying to go from bigger segment to smaller segment. So this should be less than 1. And then when you do divide that, if you'd like to write it as the decimal, that's 0.666 repeating. Okay, so for this one, figure F is this bigger one at 12. Figure G is the smaller one at 3. So again, when you're doing your scale factor, okay, we know that we should be getting smaller. Okay, 12 should be going down to 3. So again, the smaller number on top divided by the bigger number on bottom. And then this is going to give you a scale factor of 0.25. or 1/4 as a fraction. But so keep in mind, bigger to smaller, so you remember that this is going to be less than 1. And then card 5, the comparing F is this 4, okay, G is the 3, and those are corresponding sides. So we're going from F to G, so we're getting smaller. Okay, so again, where we want to go versus where we started. So 3 divided by 4, which gives us a scale factor of 0.075. Again, that's smaller than 1. And if we wanted to go the reverse, okay, so if we wanted to go G to F, then we would just flip these. Okay, so then these would be flipped over and it'd be 7.5 over 5, or 12 over 3, or 4 over 3. All right, next activity. So given some triangles here and given some information, so they tell you that AB and QR are already parallel to each other. Okay, so these lines are parallel. And then that AB is perpendicular to AE, so they're giving you that this is a right angle, which we can see in the diagram, and QR is perpendicular to QT, which we can see they've already marked as a right angle. So write a sequence of transformations, then write a similarity statement. Okay, and a similarity statement looks like this. It's like a congruent statement, except for it doesn't have the equal sign under here because they're not equal in length. Okay, so they're just similar. The sides are proportional. They can dilate to one another. So write a sequence of transformations that would take one triangle to the next, then write a similarity statement. You can pause the video while you do that and then come back. So when we do this, there's going to be a couple ways to do this, because again, you could take either the big triangle to the small or the small to the big, whichever you would like. The fact that these lines are parallel means that we'll be able to translate it without doing a rotation, because we'll be able to get QR to land right on AB at the same angle. Okay, so if you'd like to get a common vertex together first by doing a translation, then dilate, that's fine. I'm going to do the smaller triangle. I'm going to move the smaller triangle. So I'm going to translate triangle TQR by directed segment RB. Okay, so I'm going to move R to B since those are corresponding vertices. And so I'm going to get those together so that they're matching. Then I just need to do a dilation. Okay, so then I just need to figure out how much bigger this ABE is than TQR. Okay, so comparing any two corresponding parts. Okay, so any two sides that are similar. So I'm just going to compare AB to QR. So I'm just going to divide those. 8 divided by 3.2 will give me the scale factor that I need. So 8 divided by 3.2 equals, 8 divided by 3.2 is 2.5. So that's going to give me the scale factor to bring this shape to this one will be a scale factor of 2.5. So then I would do dilate. triangle TQR using B as the center and a scale factor of 2.5. So I've moved the triangle over here. Now I've expanded it, and let's just check to make sure. So do 6.8 times 2.5 to make sure that that equals the 17. So 6.8 times 2.5 equals 17, okay, which gave me that correct length here. And then let's do 6 times 2.5 to see what that is, to make sure that that's proportional. So 6 times 2.5 did give me 15. So those sides all checked out. So then you can write a similarity statement. Okay, so we know that once we dilated it, then this 6.8 side became 17, so T would land on E. We expanded this side, so 3.2 times 2.5, so Q landed on A, and then also QT was 15, so it was that exact same size. So similarity statement here, you can write out whichever triangle you want first. So I'm going to do TQR. Then put the corresponding angles together, corresponding sides together. So T goes with E, Q goes with A, and R goes with B. And how did we know that they were similar? Because there was rigid motions that took all of these vertices to coincide with these ones. And by that scale factor, we got all the sides to be the same length as these. So we were able to land it on that triangle because they were congruent after a dilation. So then would there be more than one correct way to do this? Yes, okay, because we could have taken this bigger triangle, moved it over here, dilated down. Okay, so instead of doing 8 divided by 3.2, we could have done 3.2 divided by 8. So if we wanted to take this triangle to this one, we would have done 3.2 divided by 8 and gotten a scale factor of 0.4, versus when we take the small one to make it bigger, the scale factor was 8 divided by 3.2, which was 2.5. So that's a different way to do it. You also could line up different points. So when you translate, we could have translated Q to A, or we could have translated T to E. Okay, so you just have to get one set of vertices that are corresponding put together through the translation and do a dilation. Dilation could come first, then the translation, or translation, then the dilation. Is there a wrong way to write the similarity statement? Yeah. Okay, so when we're talking different ways to write the similarity statement, you just have to line up the correct angles. Okay, so if we're taking a look at this first triangle, A, B, E, when we do the similarity statement, we have to line up the corresponding angles. Okay, so we have to go in the same order. So A goes with Q, B goes with R, and E goes with T. So you can write your similarity statement however you want, as long as those ones go in the same order. So if I'm going to do the first one, triangle BEA, that's going to be similar to, make sure you put what went with B is R, with E is T, and with A is Q. So as long as those match up correctly. So is there a wrong way to do it? Absolutely. Okay, if you lined up the wrong angles. So if I put angle, if I did RTQ for this one, because angle A is supposed to go with Q and it doesn't. So this would be wrong if you don't get the corresponding angles lined up. All right, so synthesizing this, so choosing a method for transforming one similar figure to another that you prefer. So you can dilate first or do rigid motion first, whichever you want. Okay. And in this case, it's saying that this is double the size. So we would want to, again, you could either dilate this triangle first using a scale factor of 2, then translating it. You could dilate this big triangle using a scale factor of 1/2, the flip of 2, and then translate. Okay, so kind of different ways to do it with the same outcome. Pause the video on here and you can get this written in your reference chart. Then in the lesson summary, so figures are similar if there's a sequence of rigid motions and dilations that takes one figure to the next. So in the drawing here, if we take a look at this, okay, we see that, 2.8 is bigger than 4. So this 2.8 side goes with the bigger side down here. So the 2.8 corresponds with the 5.6, and this 2 corresponds with this 4. So then we'd be able to rotate this around. Okay, so that's what they're going to say in here. If we do a 180-degree rotation, okay, that will flip this triangle over, this blue triangle over into this bigger triangle. Okay, so this will rotate it around here. So now we've got the 2 and the 2.8 here. And then remember that this was 5.6 and this was 4. So if we do a scale factor here, okay, either taking the bigger triangle by a dilation of 1/2, so reducing the size of this bigger black triangle by 1/2, okay, we'll pull this E down to D prime, and we'll pull this G down to F, because 1/2 of 5.6 is 2.8, 1/2 of 4 is 2. Or you could dilate the green triangle by a scale factor of 2, so doubling this, because if we double 2, it will be 4. So D prime will land on E, F prime will land on G. Then they are the exact triangle. So there is a rigid motion of a rotation and a dilation that will make the two triangles land right on top of each other. Okay, so that's basically what this says in a lot more detail. And so you get your corresponding angles are congruent, the lengths of opposite sides. So if figures are similar, okay, all the pairs of corresponding angles are congruent. That's a big thing. Okay, and the lengths of all the pairs of corresponding sides are in proportion, meaning they divide to the same number. Okay, so those two differences there. So corresponding angles are congruent, okay, and sides are in the same proportion. And then we also in this lesson learned about writing similarity statements. Okay, so then you wrote out these similarity statements, much like a congruent statement. Make sure the parts are lined up, the corresponding angles, and then you just use just the squiggly line.